Welcome to SDN Tech Networking Podcast, world's first human-curated AI podcast.
Okay, let's unpack this. Imagine a world where the digital locks protecting our most sensitive information, things like online banking, classified communications, could be picked almost instantly.
Yeah, it sounds like science fiction, doesn't it?
It really does. But that's the looming shadow of quantum computing. It's not that far off. But here's where it gets really interesting. A new era of quantum-safe cryptography is already upon us. We're actually building defenses before the threat fully hits.
Indeed. And that's what our deep dive is all about today, navigating this really complex landscape of quantum computing's impact on cybersecurity.
Right. So our mission for you, the listener, is to cut through the jargon, because there's a lot of it, and equip you with a clear understanding of these powerful new threats, and maybe more importantly, the innovative, sometimes pretty mind-bending solutions emerging to protect our digital world. So let's start right at the beginning. Why are quantum computers such a big deal for our current security? What's the fundamental shift?
Okay, the core threat really comes down to specific quantum algorithms. The most famous one is Shor's algorithm. This algorithm have the potential to find the prime factors of very large numbers incredibly quickly.
Okay, factoring large numbers.
Yeah.
Why does that matter so much?
Well, because our widely used public key encryption methods, think RSA, elliptic curve cryptography, or ECC, Diffie-Hellman key exchange, these are the very foundations of secure communication. TLS for websites, SSH for secure logins, IPsec for VPNs, things we use constantly. And they're all built on the assumption that factoring these huge numbers is just computationally impossible for today's computers.
Ah, okay. So Shor's algorithm basically breaks that fundamental assumption.
It completely changes the equation, yes.
So is this a problem we need to worry about today, or is it still kind of a distant future concern? I've heard this phrase, harvest now, decrypt later. What does that actually mean for data we think is safe right now?
That's a critical question, and yes, it is relevant today.
Yeah.
There are really two main types of threats here. Harvest now, decrypt later, that's happening right now. Adversaries, nation states, whoever. They're intercepting and storing currently encrypted data.
Or emails, cloud backups, everything.
Exactly. Stuff encrypted with today's standards. The plan is to just hold on to it and then decrypt it years from now once they have powerful enough quantum computers. So it's a direct threat to the long-term confidentiality of sensitive information.
Wow. Okay, so data we send today might not be confidential in 10, 15 years.
Precisely. And the second type is active quantum attacks. That's where future quantum computers could actively break things like cryptographic signatures in real time.
Allowing what? Impersonation, forgery?
Yes, impersonation, authentication forgery, tampering with data as it's transmitted. Now, fully powerful quantum computers aren't quite here yet for that, but experts anticipate machines capable of breaking, say, RSA 2048. They could be operational somewhere in the 2035-2040 timeframe.
Which, in terms of upgrading global infrastructure, is practically tomorrow.
It's the blink of an eye, really.
Okay, so to understand the solutions, we probably need to get our heads around a few basic quantum concepts. Let's start with the qubit. We all know classical bits are just 0 or 1. How is a qubit different? Why is it so powerful?
Right. A classical bit is it's either 0 or it's 1. A qubit, though, leverages quantum mechanics to exist in what's called a superposition. That means it can be kind of a mix of both 0 and 1 at the same time.
Like a dimmer switch instead of an on-off switch?
Sort of, but maybe more like a coin spinning in the air. It's neither heads nor tails until it lands. Until you measure the qubit, it holds this probabilistic mix. When you do measure it, the superposition collapses into a definite 0 or 1.
And this ability to hold multiple states allows them to process more information.
Vastly more simultaneously. That's a key part of their potential power.
Okay. And then there's entanglement.
Yeah,
That sounds even weirder. Spooky action at a distance, right?
That's the famous Einstein quote, yes. And it is spooky. Entanglement happens when two or more qubits become linked or correlated. They're linked in such a way that the state of one instantaneously affects the state of the other, no matter how far apart they are. Miles, light years, doesn't matter.
Instantaneously.
According to the theory, yes. It's not transferring information faster than light in a way you could use for communication, but the correlation is instant. And this property isn't just a cool quirk, it's fundamental. It allows qubits to share information and coordinate computations in ways that classical bits just can't. It enables that powerful parallel processing.
So superposition and entanglement, these are the key quantum tricks that algorithms like Shor's and I think another one called Grover's use.
Precisely. Shor's algorithm, as we said, uses these properties to factor large numbers efficiently, hitting public key crypto. Grover's algorithm is different. It provides a significant speed up for searching unstructured databases.
How significant?
Think about searching a huge list. A classical computer might have to look through, on average, half the items. Let's say n items. It takes roughly n2 steps. A quantum computer using Grover's algorithm could potentially find the item in roughly the square root of n steps.
Square root. So for 1,000,000 items, instead of 500,000 steps, it's 1,000.
Roughly, yes. It's a quadratic speedup. The analogy used in one paper was quite neat. Imagine finding a specific tuning fork in a room full of them. Grover's is like striking all of them at once, somehow marking the right one by, say, inverting its sound wave, and then using quantum interference so only the marked one vibrates loudly, allowing you to identify it instantly.
That's a very different way of searching.
It absolutely is.
Okay, so we get the threat, we get the mind-bending quantum principles behind it. What's the direct cryptographic response? How do we build locks that even these tools can't pick?
Right. That brings us to post-quantum cryptography, or PQC. PQC basically refers to cryptographic algorithms, new encryption methods, new signature schemes that are designed to be resistant to attacks from both classical and quantum computers.
So they don't rely on factoring large numbers anymore.
Exactly. Instead of relying on problems like factoring or discrete logarithms, which Shor's algorithm solves easily, PQC is based on entirely different types of mathematical problems. Problems believed to be incredibly hard even for the most powerful future quantum computers.
What kind of new math problems are we talking about? Are they just like harder versions of the old ones?
No, they're fundamentally different families of problems. The leading candidates, the ones NIST has been standardizing, fall into several categories. There's lattice-based cryptography, code-based cryptography, hash-based signatures, multivariate cryptography.
So like a grid?
Sort of. But imagine a very complex, high-dimensional grid or lattice structure. A key problem in lattice-based crypto, used in algorithms like Crystal's Kyber, which NIST selected, is finding the shortest vector, the shortest distance between 2 points within that incredibly complex lattice. Turns out this is extremely difficult, even for quantum computers.
Finding the shortest path in a super complex maze.
That's a decent analogy, yes. It's computationally intractable, as far as we know.
Okay, so we have these new PQC algorithms based on different math. Is deploying them just a matter of swapping out the old RSA code for the new Crystal's Kyber code? It sounds too simple.
Yeah, it's definitely not that simple. It's a massive undertaking across the entire global digital infrastructure. For many systems, a hybrid approach is being adopted, at least initially.
Hybrid, meaning using both old and new at the same time.
Exactly. You combine a new post-quantum algorithm with a current proven classical algorithm like ECC or RSA. The UK's NCSC, for instance, specifically recommends considering hybrids as an interim measure. It helps smooth the transition.
How does that help?
Well, it lets organizations start building quantum resilience now, using the new PQC algorithms, while still benefiting from the known security and maturity of the classical ones. It's a belt and suspenders approach during the migration. The long-term goal is definitely a PQC-only state, but this hybrid phase manages the complexity and risks.
Are we seeing this happen in the real world yet? Any big examples?
Oh yes, definitely. Major players are already integrating PQC. Apple is a great example. They've actually integrated quantum secure cryptography into iOS, macOS, etc. Their CryptoKit framework now supports ML-Chem.
That's one of the NIST standards, right? Based on lattices?
Yes, Crystal's Kyber is formerly known as ML-Chem, Module Lattice-Based Key Encapsulation Mechanism. Apple supports that for key exchange. And MLDSA, dilithium, for signatures. And they've integrated it with their secure enclave for extra hardware protection.
Wow, so it's potentially in the phone I'm holding right now.
It's rolling out, yes. And it's not just consumer tech. The NSA has recommendations, too. They're pushing for specific algorithms like ML-Chem 1024 and MLDSA 87 for national security systems. Their target is to have quantum resistance basically flipped on across those systems by the end of 2031.
Okay, so it's definitely happening. What about symmetric key crypto? Things like AES, which we use to encrypt files directly. Is AES broken too?
That's a good distinction. Symmetric key algorithms like AES are generally considered weakened by quantum computers, but not completely broken like public key systems.
Weakened how? By Grover's algorithm.
Yes, Grover's algorithm could theoretically speed up brute force key searches. So a common recommendation you'll see is simply to double the key size. If you're using AES 128, move to AES 256.
That restores the security margin against a Grover's attack.
That's the general consensus, yes. Maintain a sufficient security level. Interestingly, some research, including papers cited by the UK NCSC, suggests the practical impact of Grovers on AES might be limited due to overheads and other factors.
So less of an urgent panic for AES, but still something to watch.
Right. The primary urgent threat is definitely to public key cryptography, the key exchange, and digital signatures.
Okay, so PQC offers algorithmic solutions. But there's another whole approach using quantum mechanics directly for security. Quantum key distribution, or QKD. How does that work?
QKD is fascinating. It aims to establish a shared secret key between two parties traditionally called Alice and Bob, with security guaranteed by the actual laws of quantum physics. The basic idea is to encode bits of information onto the quantum states of individual photons, usually using properties like their polarization or phase. Alice sends a stream of these quantum-encoded photons over a channel which could even be public, like an optical fiber to Bob.
And what makes it secure? If someone, let's call her Eve, tries to listen in.
That's where the no-cloning theorem comes in. It's a fundamental principle of quantum mechanics. You cannot create an identical copy of an unknown quantum state. More importantly for QKD, the act of measuring a quantum state inevitably disturbs it.
So if Eve intercepts a photon to read its state,
She inevitably changes it. When Bob receives the photons, he and Alice perform a process. They basically compare notes, not the key itself, but information about their measurements, over a regular communication channel. This allows them to estimate the error rate in the transmission. If there are too many errors,
they know someone was listening.
exactly. They know Eve was likely intercepting and measuring the photons, introducing those errors. If the error rate is too high, they just discard the potential key material and start over.
A quantum tripwire.
That's a great way to put it. If the error rate is low enough, they can be confident Eve wasn't listening significantly.
So they exchange photons, check for errors, and if it's clean, they have a secure key.
Almost. After the initial photon exchange and error check, there's a crucial key distillation phase. They use classical algorithms for error correction to fix minor non-eavesdropping errors and privacy amplification to eliminate any partial information Eve might have gleaned. The result is a shared, secret key known only to Alice and Bob with a very high degree of confidence based on physics.
And then they use that key how?
They can then feed that secure key into standard classical cryptographic protocols like AES for encryption or IPsec for securing network traffic.
So QKD generates the key. Classical crypto uses it.
Precisely. QKD solves the key distribution problem with quantum security.
Sounds incredibly powerful.
Yeah.
What are the catches, the limitations right now? Doesn't sound like it's replaced everything yet.
No, definitely not. QKD has promise, but it's not a magic bullet, and it faces practical challenges. A major one is range. Photons get lost or absorbed in optical fibers over distance. Detector inefficiencies also play a role. While researchers have demonstrated QKD over impressive distances in labs, practical commercially available systems are often limited to, say, a few hundred kilometers. Repeaters are difficult.
So mostly for metro area networks or dedicated links, not the global internet yet.
Generally, yes. And it's important to reiterate. QKD is for key distribution. It generates the secret key securely. It doesn't encrypt the bulk data itself. The actual data still travels over classical channels, encrypted using the key QKD provided.
Okay, that makes sense. So bringing this back to real-world applications, how are these things, PQC and maybe even QKD, being implemented in networks today? Like with IPsec VPNs that so many businesses rely on.
Right. IPsec is a perfect example. It's ubiquitous for VPNs and securing IP traffic. Traditionally, the key negotiation part of IPsec, called IKE, Internet Key Exchange, uses algorithms like Diffie-Hellman.
Which we know is vulnerable to quantum computers.
Exactly. So that's the weak point in traditional IPsec from a quantum perspective. The actual data encryption within IPsec, though, often uses AES 256.
Which is considered quantum resistant, especially with the larger key size.
Correct. So the main challenge is securing the IKE key exchange.
So how do you plug PQC or QKD into that IKE process?
Several ways are emerging. For PQC, the IETF is standardizing extensions to IKVAVE2 to allow negotiation and use of post-quantum algorithms, often in that hybrid mode we discussed. For QKD, it's a bit different. You might have a dedicated QKD system generating keys, then you need a way to securely get those keys into the IPsec device, like a firewall or router. There are developments like specialized key management daemons, sort of like a secure key store proxy, and standardized APIs, like one from ETSI QKD 0110, that define how a key management server within the QKD network can talk to the security device.
Okay, so an API connects the QKD magic box to the network firewall. But that API connection itself needs to be secure, right? If it's just sending the super secret quantum key over a regular network.
You've hit on a crucial point and a current challenge. Often, that API connection is secured using standard TLS.
But wait, doesn't standard TLS use RSA or ECC for its own key exchange? The very things that are quantum vulnerable.
Exactly. So if you're relying on standard TLS to protect the delivery of your quantum-generated key, an attacker could potentially use a harvest now, decrypt later attack on that TLS connection to eventually steal the quantum key.
So you could have a quantum-proof key delivered over a non-quantum-proof channel. That seems problematic.
It is, which means for maximum security right now, especially against that harvesting threat, the QKD system and the security device, like the firewall, need to be in close proximity, usually within a physically secure environment. Think a locked rack, a secure room.
So the key exchange over that API happens over a protected short link, not the public internet.
That's the recommended practice for high assurance. Once the key is securely inside the IPsec device, then you can configure the IPsec tunnel using that key and monitor it to verify it's quantum secured, as some systems label it.
Fascinating. So the physical world still intrudes on the quantum one.
Security often comes down to layers, physical and digital.
This whole deep dive has been focused heavily on cybersecurity, breaking, and securing encryption. But quantum computing has potential way beyond that, right? What else is on the horizon?
Oh, absolutely. Cybersecurity is just the most immediate disruptive application because it breaks something we rely on now. But the potential is much broader. Quantum machine learning, or QML, is a huge emerging field.
Using quantum computers for AI.
Essentially, yes. Trying to leverage quantum phenomena like superposition and entanglement to process data and potentially run machine learning algorithms much faster or in fundamentally new ways. People are designing parameterized quantum circuits that they're starting to call quantum neural networks. It's early days, but the potential is there for breakthroughs in complex optimizations, pattern recognition.
How might that apply back to cybersecurity then? Maybe not encryption, but other problems, like detecting sophisticated DDoS attacks.
That's a great thought. While current cutting-edge DDoS detection often uses advanced classical AI, we saw research using things like generative AI combined with other techniques to get high accuracy. You can imagine a future where QML could analyze vast amounts of network traffic data in ways classical systems just can't, maybe identifying subtle distributed attack patterns much faster or more accurately.
Processing immense data sets to find needles in haystacks.
Exactly, revolutionizing anomaly detection, threat intelligence.
Yeah.
That's the hope.
And then there's the really big picture idea. A quantum internet or quantum networks. What does that even mean?
Yeah, that's looking further ahead. The vision is to interconnect quantum computers, quantum sensors, and other quantum devices. These networks wouldn't just transmit classical bits, they could transmit qubits, perhaps entangled qubits, over long distances.
Enabling what? Things beyond QKD.
Potentially, yes. Things like distributed quantum computing, where multiple smaller quantum computers could collaborate on a problem too large for any single one, or enhanced sensing capabilities. And, of course, advanced forms of secure communication. Huge challenges remain, obviously. Maintaining qubit coherence, keeping them quantum over long distances, is incredibly hard, dealing with signal loss.
Same problems QKD faces, but maybe harder.
Likely, yes. But major players like Cisco are actively researching this. They're looking at modular, scalable quantum network architectures. They're even building simulators, digital twins like QNet Lab, to model these future networks and train people. The idea is likely that classical and quantum channels will coexist.
Offering different services, maybe quantum channels for super secure links or entanglement distribution.
That seems to be the direction, yes. Creating new dimensions in networking.
Wow, what an incredible deep dive. It really feels like we're on the cusp of a major shift. From science fiction to, well, applied engineering and looming reality, we've seen these serious immediate threats from quantum computing to our current digital security, but also the really ingenious ways scientists and engineers are already building defenses, PQC, QKD, harnessing those same weird quantum properties for protection.
It is fascinating, and it really underscores the pace of change.
It absolutely does. It's almost dizzying.
And this brings us back to a crucial point for you, the listener. We've talked a lot about threats and solutions, but quantum attacks, especially that harvest now, decrypt later threat, aren't some far-off hypothetical. They are relevant now. So the question to really ponder is, What critical data or systems do you have right now, data that needs to remain confidential for 10, 15, 20 years or more? If that data were exposed years from now by a quantum computer, what would the impact be? Significant harm. And if the answer is yes, what proactive steps can you or your organization start taking today to protect it with quantum safe measures? Hybrid approaches, inventorying critical data. It's really about starting that migration journey now rather than waiting until the quantum decryption capabilities are fully realized, because by then, for harvested data, it's already too late.